So we are going to be reviewing the concepts. We're going to do some problems, everything for your test that is on Monday. If you're one of the lucky classes that actually gets to have me do it in class today, congratulations. Yay. The other people get to watch a video because they're not in class. Yay. Okay, so where we need to start is by looking at the assignments that'll be checked for your notebook check. We have quite a few assignments this time. So this goes all the way back. Ooh, not all the way. Come on. Okay, so the first assignment that y'all had in this section was 5J, Magnetism Notes and Practice. That's where we got things started off. Then we did chapter 24, number 1 through 9. Then we had the 5K generators and motors notes. Then we did the magnets inquiry lab, which was on the computer. Remember that this lab is a quiz grade all of its own. Then we had chapter 24, number 19 through 24. Starting with the ones I've already done. And then I have chapter 24, 25 through 33. And I got chapter 25, 1 through 10. And chapter 25, 36 through 43. One thing that's not on here, but I'll fix that. You need to have the second part of the lab that we did with where we created the motors. Unless you are in second period, because second period we had problems. Okay. Everyone else, that's all the assignments that'll be on the notebook check. And for everyone but second period, remember you had 2 labs that are worth quiz grades all on their own. Okay, remember this is available on the internet, so you can look it up on your own. But it starts way down here with the 5K, or 5J.
5K or 5J?
5J is where it starts.
So you've taken 5J?
Yes. Starts all the way here at 5J. Then chapter 24, 1 through 9, then 5K, then the magnet inquiry lab, then the chapter 24, 19 through 24, 25 to 33, chapter 25, 1 through 10, and chapter 25, 36 through 43. All right. All right, so when we're talking about magnetic fields, so looking up here, these are things that you should know or have in your notes. We don't have a ton of time since it is a half day, so I'm not going to pause and stop and explain everything and wait for everyone to copy everything down. But I will go through this, and of course, I'm going to post this video so that you can see it. Okay, so this is something that we should know. We should know that when we have a magnet, a permanent magnet, the field lines go out of the north and into the south. We should know that B stands for... That's right, magnetic field. The N is north, the S is south. Okay, now there were several right-hand rules that we talked about. So you need to know when to apply each one. So this is the right-hand rule for just what magnetic field comes from a current-carrying wire. So if you put your thumb in the direction of the current on the wire, the field goes around the wire like this, okay? That can be added on to an armature, which is just a set of coils like what we made in the lab the other day. You put your thumb in the direction that the current is going, and the field will be where your fingers curl around, okay? So we got that. And then we get to the one that we practiced extensively in class, so I'm pretty sure y'all know this one. But this is the one for the force that you experience when you have a current going through a wire that is in a magnetic field. So you put your thumb of your right hand in the direction of the current that's in the wire. Your fingers will point in the direction of the magnetic field, so from north to the south, and coming up out of your palm in this case, or it could be going left out of your palm, it's whatever direction your palm is pointing, is the direction of the force. Okay? So here we have a couple of examples that you can run through with me. So we're going to look at the field out of the page. Remember, the dots mean that it's coming towards you like the front of an arrow. The X's means that it's going into the page like if you're looking at the back of an arrow. Okay? So everyone practice with me right now. Take your right hand, put it in the direction of the current. Your right hand in the direction of the current. Okay? So my right hand is in the direction of the current. The field is out of the page, meaning it's going backwards towards where y'all are sitting, right? That means that the force comes out of my palm and goes which direction? Down. Okay, so down. Does that make sense? Okay, we're going to do the other one again. So again, current for your right hand. Then field is into the page. Which way is my palm pointing? Up. Okay, so notice I'm facing the back of the room, but my palm still went up doing the right hand rule, right? Y'all are facing the front of the room, but y'all do the right hand rule, and y'all also get up. So that's the whole thing. As long as you're using your right hand, it works. Okay? Now, when we're calculating this force, F stands for force, right? What does I stand for? Current. What does the L stand for? The length of the wire. What does the B stand for? Magnetic field strength. And theta is? It's not always 90. So theta is the angle between the magnetic field and the current. So if it's perpendicular, like right and up or something like that, that will be 90. If they give you an angle, put the angle in.
Oh, I got you.
Okay? Yeah, for the most part. All right. So, example problem. We want to calculate the strength of a magnetic field. So it says a straight wire carrying a current of 5 amperes. So what's the current? That's right. I is equal to 5.0 amperes. It's in a uniform magnetic field that is oriented at right angles. So right angle is how many degrees? Okay? It says 0.10 meters of the wire is in the field. So what is that telling me? And then it says the force on the wire is? What's the unknown? B. The equation is F equals I L B sine theta. What's your question?
I was wondering, because I think on one of the questions that we had, the length had a different unit. So I was just wondering if we have to be here.
Okay, so the question that was asked is, when I use this equation, does the length have to be in meters? The answer is yes. So it has to be in standard units. The force is newtons, the I is in amperes, the L is length in meters, the B is magnetic field in Teslas. If you have micro Teslas, you got to convert to Teslas. If you got millimeters, you got to convert to meters. Okay, so we're solving. We got 0.20 is equal to 5 times 0.1 times B sine 90. All right, the 5, the 0.1, and the sine 90 are all doing what to B? They are multiplying. So to get B by itself, I need to do the opposite of multiplying, which is divide. So I'm going to divide both sides by 5 times 0.1 times sine 90. 5 times 0.1 is 0.5. 0.2 divided by 0.5 is 0.40, I think. Pretty sure that's what it is. Anyone got confirmation for me? Because I gotta take like 5 minutes to open up this calculator. No, no one gonna do it. I'll just continue waiting. So 0.2 divided by 0.5 is what?
I got 4.
0.4, good. I do know math. So we got B is equal to 0.4. How many sig figs do I have? 2 sig figs. So do I have 2 sig figs in my answer? No. So it needs to be 0.4. 0. What's the unit for magnetic field? Capital T for Teslas. All right. So the next equation that we had was the force of a magnetic field on a moving charged particle. So we said that anytime that we have moving charges, like a current, we're going to get a force if it goes through a magnetic field. So if I have this, it doesn't have to be just a current. It could be a single particle that's moving. So the force is equal to Q, which is the charge, times V, which is the velocity, times B, which is the magnetic field, and again, sine theta. So we'll look at our givens. It says a stream of doubly ionized particles, which means that they're missing 2 electrons and thus carries a net positive charge of 2 elementary charges. Okay, that's telling us the charge, right? When it says that it's got 2 elementary charges, what does that mean? What's an elementary charge? Well, it's pretty small, but that's not going to give me my answer. An elementary charge is specifically telling me that it's the same charge as an electron or a proton. So it's 2 times the charge of an electron or proton. So does anyone remember what the charge of an electron or proton is? 1.6 times 10 negative 19 coulombs. Okay? So that's what the charge is. I know this is one of y'all's homework problems, but a lot of people didn't do this correctly, so make sure that you're making that correction now. Okay, so that was Q. It says perpendicular, so perpendicular tells us that theta is what?
90 degrees.
90 degrees. It says the magnetic field is 9 times 10 to the negative 2. So that's B. 9 times 10 to the negative 2. And I missed one. What did I miss? I missed velocity. Okay, so I'll just scroll down a little bit more. We got V is equal to 3.0 times 10 to the 4th meters per second. What's our unknown? How large is the force? What is our equation? All right, So we're looking for force. This one will be easy. We'll just end up multiplying, right? So F is equal to, Q was 2 times 1.6 times 10 to the negative 19th times V was 3 times 10 to the 4th times B, which is 9 times 10 to the negative 2 sine 90. Now this one I need a calculator for. I can't do all those numbers in my head. All right, we got 2 times 1.6 double E negative 19 times 3 double E 4 times 9 double E negative 2 trig sine 90. Enter. We had 8.64 times 10 to the negative 16th. How many sig figs? 2. That's going to round out to 8.6 times 10 to the negative, I said 14, right? Oh, 16 newtons. A very, very tiny force. All right. We'll move on. Induced EMF. So EMF is the same as what other thing that we've talked about? Say it louder. Voltage. So EMF is just voltage. So whenever I put a current carrying wire, or I'm sorry, whenever I put a wire through a magnetic field and I cut the field lines. So if I just have a wire, no current going through it at all, and I cut magnetic field lines with it by applying some force, because it's not going to go through by itself, right? You know, things don't tend to move on their own. You have to apply some force. So if I put a force on this wire and I make it cut these electric field lines, it's going to induce a current and thusly a voltage in that wire. Okay? So we have EMF is equal to B, which is magnetic field, times L is the length of the wire, times V, how fast you're moving it through the field, times sine theta. Again, if it's perpendicular, it's 90 degrees. If it's less, you put in the angle, right? Okay. So this was an example from the book. It says a straight wire is part of the circuit that has a resistance of 0.50 ohms. The wire is 0.20 meters long, moves at a speed of 7 meters per second, perpendicular to a magnetic field of strength 8 times 10 to the negative 2 Teslas. What's the EMF in the wire? So, write all of our givens. We got resistance is 0.50 ohms. The length is 0.20 meters. The velocity is 7.0 meters per second. The magnetic field is equal to 8 times 10 to the negative 2 Teslas. Theta is going to be 90, because it said perpendicular. Okay, the unknown. The first unknown I'm looking for is EMF. The second unknown is the current. And we're actually not going to do C. It's going to be just a repeat of what B is. Okay, so the equation, EMF is equal to what? All right? Okay, and then I is just equal to P over R, right? Or in this case, EMF over R, but they're the same thing, right? Okay, solve. I got EMF equals B, which is 8 times 10 to the negative 2, times L, which is 0.2, times V, which was 7, times sine theta, which is going to be 1. All right, calculator, we do 8 double E negative 2 times 0.2 times 7. Get 0.112. 0.112 to 2 sig figs is 0.11 volts. And then, of course, I is V over R, right? So I is just equal to 0.112 over the resistance, which was 0.5. So go to the calculator, divide by 0.5, and we get 0.224, which is really 0.22 amperes. All right. Make sense? All right. A lot of people skipped over this equation whenever they were doing this problem. So this equation wasn't in the notes, but it was in the section right before you did the problems for your homework. If something doesn't make sense, you should probably go and look at the little section before, right? Okay. It says the power produced by an AC generator is the product of the current and the potential difference. Because both the current and the potential difference vary, the power in the circuit varies. The graph at the bottom, figure 8, shows power and all that. But what we find is that the average power is half the maximum power. So power for an AC circuit is half of the maximum power. So, for instance, in question number 7, which was a homework problem, this is in chapter 25, it says the average power used is 0.75 watts. What's the peak power? Okay, so we got, this is my given. We got 75 watts. That's going to be the average power. Unknown is PAC max. The equation is right here. We're running out of time, so I'm trying to get this in. The solving, we just have 75 is equal to 1/2 PAC max, which tells me that PAC max is equal to 150 watts. Put this on here just because I know for a fact that people missed this on the homework. Okay. 150 watts, yes. All right, these last little examples right here, they are super, super simple to where I probably don't even need to go over it. I just wanted to make sure that you looked at them. If I'm looking for the effective potential difference, I'm using this equation. If I'm looking for the effective current, I use this equation. If I want to then figure out the resistance, it's just R equals V over I. All right. One more thing that's going to be on the test. I know y'all are leaving and y'all are going to miss this. One more thing that's going to be on the test. You need to know how electric motors work. If you look at the video that explained how electric motors work, you'll be fine. If you did your 5J and your 5K and you actually did it, you'll be fine. If you didn't do those or you copied off of someone, you have no idea what it is, you will fail. All right.